If you've spent years in the trenches with C++03, you know the raw pointer. It's powerful, but man, it can be perilous. Well, the language has changed a lot. So today, we're going to trace the journey from the Wild West of manual memory management all the way to the modern C++ philosophy, a world of clear, safe, and expressive code. You'll see this isn't just about learning new syntax. It's about fundamentally changing how we think about writing C++. First things first, let's get this straight. The point here isn't to get rid of pointers entirely. It's about getting rid of the guesswork. You know that feeling, that little voice in the back of your head asking, who owns this memory? Who's supposed to delete this thing? That ambiguity, that's the real enemy. It's the source of so many bugs. And the whole point of this modern C++ revolution is to bake the answers to those questions right into your types. Take a look at this. Come on, we've all written this exact function 1,000 times. But as innocent as it looks, this one line is a ticking time bomb of questions. When I call this function and get a pointer back, is it mine now? Am I responsible for calling delete on it? What if an exception gets thrown before I can even save it anywhere? That, right there, is ownership ambiguity, and it's the root cause of countless bugs we've all had to hunt down. So let's really spell out the dangers we all used to live with. And these aren't just some abstract theoretical problems, right? These are the real-world bugs that have cost us who knows how many hours of debugging and kept us up at night. And here they are, the four horsemen of manual memory management. You've got your memory leaks, right? You forget to delete, and you just watch your app's memory usage creep up and up. Then there's the double free, that classic crash when two different parts of your code think they own the same thing and both try to delete it. Yikes. Then you have dangling pointers, where you're using memory that's already been freed, leading to all sorts of chaos. And of course, the one that causes all the others, ownership ambiguity. This is the original sin. I'm sure every single one of us has lost a weekend debugging at least one of these. So how do we fight back against this chaos? Well, the first big revolution is a concept I like to call smart ownership. The whole idea is simple. What if we let the language itself manage the resources for us, automatically and safely? Meet your new best friend, standard unique pointer. Seriously, the name tells you everything you need to know. It represents unique, exclusive ownership. When the unique pointer goes out of scope, poof, the resource it owns is automatically deleted. And here's the best part, the real kicker for us C++ devs. It's a zero overhead abstraction. In almost every case, it's the exact same size as a raw pointer. No performance hit. And this slide, this just shows you how massive that one little change can be. On the left, you've got the old way, a linked list with a raw node star. This thing is so fragile, you need a perfect destructor, crazy copy logic, it's a minefield. But now look at the right. All we did, the only thing we did was change node star to standard unique pointer of node. That's it. Now, each node owns the next one. When the head gets destroyed, it triggers a clean, safe, recursive teardown of the whole list. No custom destructor needed, it just works. And this leads us to the promised land, the ultimate goal, the rule of zero. The idea is so elegant. When all your class members are self-managing types, things that clean up after themselves, like standard unique printer or standard string, then you don't have to write any of the special member functions yourself. No dostructor, no copy constructor, no assignment operator. None of it. The compiler-generated versions just work perfectly. It's really the peak of modern C++. You literally write less code and get more safety in return. Of course, unique pointer isn't the only smart pointer out there. It's got a sibling, shared pointer. But the choice between them should be pretty simple. Think of unique pointer as your default, your go-to. It's for when one thing owns another. It's lightweight, it's fast. You should only reach for shared pointer when you genuinely need shared ownership, when multiple equal owners need to keep an object alive. It comes with some overhead, like a reference count, so you just want to use it when you really need it. Now, we've talked a lot about safety, but this is C++. We care about performance. A lot. So the second revolution is all about making sure these modern features don't just make our code safer, but also faster. And I mean, sometimes dramatically faster. For decades, we were all taught that passing by const std string n was the right thing to do. But it has a secret hidden cost. If you have a string literal, or a C-style string, and you pass it to that function, the compiler has to create a temporary std string object, which often means a heap allocation, just to call the function. We're paying for an allocation just to get a read-only view of some characters. That's crazy. Well, C++17 gives us the solution, standard string view. And it totally solves this problem. It's a super lightweight, non-owning object. It's really just a pointer and a length. That's it. You can create one from a C-style string, a standard string, a literal, anything with zero allocations. It's the perfect tool for any function parameter that just needs to look at a string without owning it. And speaking of unnecessary costs, let's talk about copying. We all know it's expensive for large objects, but just how expensive are we talking? What's the real price we pay compared to the modern alternative? Well, this table lays it bare. Copying, as you can see, is an O of n operation. The cost just grows and grows in a straight line with the size of your data. Why? Because you have to allocate new memory and then carefully copy every single element over. But look at moving. It's O of 1, constant time. The line is flat. The cost is the same whether the object is tiny or gigantic. So, how on earth is that possible? Because a move doesn't copy the data. It's not a duplication. It's a heist. It can be over 10,000 times faster because it just steals the internal resources. Imagine you have a vector with 1,000,000 elements. A move operation doesn't copy those 1,000,000 elements. It just yanks the pointer to that big block of memory out of the old vector, shoves it into the new one, and leaves the old vector empty. It's brilliant. And all of this, move semantics, unique PTR, string view, it all comes back to the core philosophy of C++. It's Bjarne-Stroustrup's zero overhead principle. The idea is what you don't use, you don't pay for. And just as important, and what you do use, you couldn't hand code any better. These aren't clunky, slow abstractions. They are precision tools that give you safety and power, often at a cost that's even better than what you could do by hand. All right, so we've seen the building blocks, the smart pointers, and move semantics. Now, let's see how we can snap these pieces together into powerful, practical patterns that make even complex, real-world code so much simpler. These tools make so many classic C++ patterns cleaner and safer. You know the pimple idiom for hiding implementation details? Trivial with a unique pointer. What about managing old C-style resources, like a file star from fopen? You can wrap it in a unique pointer with a custom deleter to make sure it's always closed. And storing different types of objects in a container? A vector of unique pointer to base is now the standard, safe, and efficient way to do it. When you get right down to it, this isn't just about learning a few new library types. It's about adopting a whole new philosophy for how you write C++. A philosophy that's based on expressing your intent directly in your code. So here's a really practical mental model you can start using like today. When you're writing a function parameter, just run through this decision tree. Do you just need to read a string? Use string view for amazing performance. Do you need to transfer ownership into your function, making it the new owner? Pass a unique pointer by value. And for most other big, complex, read-only objects, the classic pass-by-const reference is still your friend. All right, let's boil this whole journey down to a few key habits. First, replace your raw new and delete calls with make unique. Second, just default to unique PTR for all your ownership needs. Third, use string view for your non-owning string parameters. And finally, always structure your classes to aim for that beautiful rule of zero. These 4 habits alone will completely transform your code. So you see, by moving from these ambiguous old pointers to modern expressive types, we're doing so much more than just preventing bugs. We're building systems that are more robust, way easier to maintain, and often a heck of a lot faster. Your daily question is no longer, who is supposed to delete this? With all that mental energy freed up, the real question becomes, what are you going to build next?